focusing especially on the comparison of and optimization of simple RNN and LSTM architectures. Time series forecasting has become increasingly crucial across various sectors, from financial markets predicting stock trends to production planning in manufacturing to environmental monitoring for climate patterns. Our ability to accurately predict future values based on historical data can significantly impact decision making and planning processes across these industries. In this project, I have undertaken a comprehensive exploration of different neural network architectures, especially comparing the performance of simple recurrent neural networks and LSTM networks. My primary goal was not just to implement these models, but to understand their strengths, limitations, and optimize their architectures for better prediction accuracy. The foundation of our analysis, uh, I have chosen a synthetic monthly production data set. The foundation of my analysis rests on a synthetic monthly production data set spanning from January 2000 to December 2022. This data set is particularly interesting because it provides us with a clean, consistent time series that's ideal for testing and comparing different neural networks architectures. The data is structured with two primary columns: month formatted as year and month, and production containing numerical values representing monthly production rates. What makes this dataset particularly suitable for our analysis is its regular monthly intervals and clear linear patterns. The consistency in data collection and the absence of significant gaps or anomalies allowed us to focus fully on the performance differences between our neural network architecture rather than dealing with data processing challenges. And when it comes to simple RNN with signed data implementation, my initial approach involved implementing a simple RNN model using a carefully constructed data set of 1000 points representing a sine wave with added Gaussian noise. This addition of noise was crucial as it better represents the real-world data scenarios where perfect patterns rarely exist. We split this data using an 80-20 ratio, allocating 800 points for training and 200 points for testing. The architecture of my simple RNN model consisted of three primary layers. The input layer was designed to accept sequences of shape none, comma 1, allowing for flexible input lengths. This fed into a simple RNN layer with 10 units, chosen to capture temporal patterns while maintaining model simplicity. The final dense output layer with a single neuron completed our architecture, resulting in 131 trainable parameters. Training was conducted over 100 epochs using the Adam optimizer and mean squared error as our loss function. The results were quite interesting. The uh, the results were quite interesting as we achieved a training loss of 0.010 and a validation loss of 0.015, indicating minimal overfitting. However, this relatively simple architecture did reveal some limitations, particularly in terms of noise sensitivity and handling number sequences. And now when it comes to LSTM neural network, during my implementation of the simple RNN, I have encountered two significant challenges that are common in recurrent neural networks: the vanishing gradient problem and the uh, exploding gradient problem. The vanishing gradient problem occurs when the gradient becomes extremely small during backpropagation, effectively preventing the network from learning long-term dependencies. Conversely, the exploding gradient problem happens when these gradients become extremely large, making network more unstable. When performing the backpropagation of errors through wind in auto-associative recurrent networks, leaf auto-associative networks included the gradient vanishing problem occurs, meaning that the gradients or partial derivatives used to modify the weights of the model shrink extremely small, thus preventing learning within the network. This is even more apparent when many integrated sequences are very long because the gradients become very small as the RNN moves back through the time step, which is a cause of concern in terms of dependent capturing with an endeavor to minimize distance across long sequences. Important issues with the vanishing gradients are almost no update flow into the network cellular layers and it fails to retain long-term dependencies which are important for process memory. Some of the problems involve when gradients are propagated back, which makes these gradients exponentially smaller, making the learning rate decrease rapidly or stop. And when it comes to the exploding gradient problem, the vanishing gradient problem occurs in the auto-associative neural network and in particular in recurrent neural networks through mistake weight back propagating. This is due to the gradients that the loss function used to update the weights in the model becoming immensely small. Because of this, the weights are updated to moderate levels, thus slowing learning in wider network. This is particularly true when normalizing in RNNs that have many integrated sequences of data. They get smaller moving back over the time, steps that make it a little challenging for the model to minimize distance over lengthy sequences of possible testing. The essential problem with fading gradients is that the initial layers in the network receive merely a hint of information. Its disadvantages is in the failure to encode the long-term dependencies, feature that is crucial for process step recall. Simple RNNs also show several limitations that impact their performances. They struggle with long-term dependencies, had limited memory capacity, and showed significant gradient instability. The computational complexity increased substantially with sequence length and the models with highly sensitivity to initial parameter values. This is where LSTM networks prove their worth. LSTMs introduce a sophisticated self-state architecture with its three types of gates. Forget gates that devise with information to discard, input gates that determine what new information to restore, and output gates that control the information to the output. This architecture effectively addresses both gradient problems and provides superior memory retention capabilities. And you can see the difference between the vanishing gradient and the exploding gradient right here. I'll give you a minute to check that out. So next we are going to discuss the limitations of simple RNA neural network. Despite being used for sequential data, simple RNN has a number of drawbacks that impair its performance, especially when it comes to applications requiring long-term memory. And also challenges with long-term dependency. The vanishing gradient problem cannot allow simple RNNs to learn and make it possible to consider the dependencies of across great stretches, meaning the model drops the initial information as it unloads. The limited memory capacity is the simple RNN uses a hidden state at all times, but due to its lack of an architecture that allows for a compartmentalized location where data can be stored and processed through a loop, For a long duration, it lacks the capacity to memorize for long. This greatly reduces the capability of the system to perform tasks that require extended duration memory within their algorithms. And when it comes to gradient instability, simple RNNs are not immune to explode gradients, which are somewhat similar to the vanish gradient problem. This is even more evident in deep networks where sequence length is exceedingly massive. For this reason, optimality may cause disability. Right here, you can see the diagram of a regular neural network. And now, when it comes to the computational complexity, LSTM and simple RNN models are good at long dependencies, though simple RNN is computationally intensive with the long sequences at the hidden state has to be completed at each step, slowing up training. And when it comes to sensitive to initialization, it was also noted that the work showed that the reliability of the network depends greatly on the recommended weight start values. The speed reduces down or the model may not learn sufficiently if it's not correctly initiated or initialized. So, so now let's go through how the LSTM neural network can provide powerful solutions to both gradient problems, so vanishing gradient problem and exploding gradient problem, and address the limitations of the simple RNA neural network. In conclusion, we can say that the problem with gradients and limitations of simple RNN are overcome by LSTM neural network being introduced in the paper. Similar to simple RNNs, LSTM is a kind of recurrent neural network that was designed to overcome those restrictions and also vanish and exploding gradient problems. When it comes to resolving the vanishing gradient issue, extra cells of LSTMs can let a gating unit regulate what data will flow through the network. The other indispensable components of LSTM include so-called cell state, a form of memory that can be passed along the time memory-related mechanisms, which are the forget gate, input gate, and the output gate of the LSTMs, define which information of the input to forget or keep in order to solve for vanishing and exploding gradients. The forget gate decides which of the previous memory to ignore, and this type of memory input regulates how much data could be taken from its memory to update it with the current data. In this learning process, each stage asks the output gate what information to disclose, and also it also assists to overcome the vanishing gradient problem because the cell state permits the gradient to pass through directly over large time intervals. And now resolving the exploding gradient issue. This is because LSTMs also do not have an exploding gradient that comes in with a basic propagation implementation. There are also other things such as tricks like gradient clipping applied to try to keep a gradient small and hence try to train the model slowly. And uh, I hope you have some knowledge about dealing with RNN drawbacks. Let's go through simple RNN drawbacks in a minute.